Hidden in the dry dirt of the Australian outback is a pile of rocks worth more than $8 billion that is actually radioactive. This is the Nolans Bore Rare Earths project, and it is a massive engineering gamble located 135 kilometers north of Alice Springs. Right now, 56 million tons of rare earth minerals are sitting under the sand, containing the neodymium and praseodymium needed to power every electric vehicle on Earth. Engineers are planning to dig a hole 225 meters deep and build a high-tech refinery in a place where the temperature can melt rubber, but with radioactive waste and a severe lack of water. Can this remote mine actually survive the challenges of the desert? Back in 1994, a group called PNC Exploration was flying over the Northern Territory looking for uranium. They noticed a huge spike in radiation on their maps and decided to land their planes to see what was causing it. They found veins of rock several meters wide that were filled with crystals. A few years later, in 1999, a company called Arafura Rare Earths took over the site to see exactly what was hidden there. They spent the next 26 years drilling more than 90,000 meters of holes into the ground. They discovered that these rocks were not just a little bit special, they were part of one of the largest rare earth deposits ever found in the world. For decades, the project sat waiting because the world was not yet ready for the green energy revolution. Now that every car company is trying to move away from gas, this old discovery in the middle of nowhere has suddenly become the center of a global power struggle. But how do you actually turn a radioactive rock in the desert into a high-tech motor part? The engineering journey starts at the very edge of the giant pit. To get the minerals out, engineers have designed an open-cut mine that will cover 135 hectares of land. Every single day, massive trucks that are as tall as houses will drive down into the earth to collect the ore. The plan is to dig up 7,600,000 tons of material every year. Out of all that rock, only about 1 million tons is actually the rare earth ore they want to keep. The rest of the rock is just waste, and it gets piled up into 6 giant mountains called waste rock dumps. These dumps will stand 50 meters high, which is about the size of a 15-story building. The engineers have to plan these piles carefully so they do not fall over or blow away in the wind. Once the ore is out of the ground, it goes to the first processing station called the Beneficiation plant. This is where the real mechanical work happens. The rocks are dumped into a giant jaw crusher. Think of this machine like a pair of massive steel teeth that can crush a rock the size of a television into pieces no bigger than 50 millimeters. This is just the first step. Those 50-millimeter rocks are still too big. They are sent into a ball mill, which is a huge spinning drum made of steel. Inside this drum, there are thousands of heavy steel balls that crash against the rocks as the drum spins. It is incredibly loud and creates a massive amount of vibration. The goal is to grind the rock into a powder that is as fine as the flour you use to bake a cake. Why do they do this? Because the rare earth metals are locked inside tiny crystals called apatite and fluorapatite. To get them out, you have to break those crystals apart completely. After the rock is turned into a fine powder, it is mixed with water to create a thick soup called a slurry. This slurry is pumped into flotation cells. This is a very cool engineering trick. Engineers add special chemicals to the water that only stick to the rare earth minerals. Then, they blow tiny bubbles of air through the bottom of the tank. The rare earth particles grab onto the bubbles and float to the top like foam in a bubble bath. The junk rock, which is mostly made of sand and common stone, stays at the bottom. The workers scoop the foam off the top, and now they have a concentrate that is much stronger than the rock they started with. This process takes the amount of rare earth oxide from about 3% all the way up to 6%. It might not sound like a lot, but it means they have half as much waste to deal with in the next step. But the real challenge is just beginning, because the minerals are still stuck in a chemical bond. This is where the project moves from simple mining to advanced chemical engineering. Most rare earth mines just use huge amounts of acid to dissolve everything, but Nolans Bore is special because it has a lot of phosphate. The engineers decided to use a process called pre-leaching. They take the concentrate and wash it with phosphoric acid. This acid is very smart. It dissolves the calcium and the phosphate but leaves the rare earths behind in a solid form. This reduces the weight of the material even more before they use the really heavy chemicals. By doing this, they save money on acid and make the whole process much more efficient. However, The rare earths are still being stubborn, so the engineers have to turn up the heat. They take the solid material and mix it with concentrated sulfuric acid. Then, they put it into a giant machine called a sulfation kiln. This is a long spinning tube that is heated to 250 degrees Celsius. At this high temperature, the acid cracks the minerals open. It is like a chemical explosion happening very slowly inside the kiln. The result is a dry, crumbly material where the rare earths are finally loose, but they are still mixed with everything else. To separate them, the engineers wash the material with water. The rare earths dissolve into the water, creating a green-colored liquid. But there is a huge problem. This liquid is also full of uranium and thorium, which are naturally radioactive. If they do not get these out, the whole project will be a disaster for the environment. This is where the most amazing piece of technology at the mine comes into play. It is called the VSEP system, which stands for Vibratory Shear Enhanced Processing. Normal filters work like a sieve you use in a kitchen. If you try to pour a thick liquid through a normal filter, the holes get plugged up almost immediately. This is called fouling. But the VSEP machine is different. It does not just sit there. It vibrates the entire filter stack 50 times every second. This vibration is so fast that it is just a blur to the human eye. The vibration creates a massive amount of shear force at the surface of the filter. This force is actually 200 times stronger than the gravity of the Earth. It shakes the radioactive particles and the solid waste away from the filter holes, allowing the clean liquid to pass through. The machine moves back and forth about 2 centimeters in a spinning motion called torsional oscillation. Because it is shaking so hard, the filters never get clogged. This allows the engineers to recover more than 90% of the phosphoric acid and turn it into a clean fertilizer that can be sold to farmers. This one machine turns a waste problem into a product that helps pay for the mine. But how they actually get the neodymium and praseodymium out of that liquid? They use a process called solvent extraction. This involves hundreds of giant tanks filled with 2 different liquids that do not mix, like oil and water. The rare earth liquid is pumped through these tanks, and special chemicals in the oil grab the specific metals they want. It is like a high-speed game of tag happening at a molecular level. By the end of this long line of tanks, the engineers have a very pure liquid that only contains the target elements. They then turn this liquid back into a solid powder called NdPr oxide. This is the magic dust that makes modern life possible. But why is the world so obsessed with these specific metals? It all comes down to the physics of magnets. Neodymium and praseodymium are used to make the strongest permanent magnets ever created. If you have a normal magnet on your fridge, it is pretty weak. But a neodymium magnet is so strong that it can lift thousands of times its own weight. In an electric vehicle motor, these magnets are the secret to performance. Because they are so powerful, engineers can make the motors much smaller and lighter. A motor using these magnets can be 70% smaller than a regular motor while still having the same amount of power. This means the car is lighter, which helps the battery last longer. These magnets also stay strong even when the motor gets very hot, which happens when you drive at high speeds for a long time. Without these minerals from the Australian desert, electric cars would be heavy, slow, and would not be able to drive very far on a single charge. Building this massive factory in the Outback requires a huge amount of infrastructure. The project is located in a place where there is almost no water and no power grid. To solve the water problem, the engineers had to search deep underground. They found a water source in the southern basins, which is about 25 kilometers away from the mine. They are building a series of deep wells and a long pipeline to carry the water to the site. But this water is not pure, so they have to build a reverse osmosis plant to clean it before it can be used in the chemical process. To power the whole operation, they are building an 18.5 megawatt power station right on the site. This power station will run on natural gas, brought in through the Amadeus gas pipeline, which luckily passes right through the project area. But the engineers want to be even cleaner, so they are adding solar panels and wind turbines to create a hybrid energy system. Their goal is to eventually reach net zero carbon emissions by the year 2500. They also have to build a place for the workers to live. Since the mine is so far from any town, they are constructing a whole village with enough room for hundreds of people. During the peak of construction, there will be 650 people living there. They will have their own kitchens, laundry, and even a gym to stay healthy in the desert heat. Managing a small city in the middle of nowhere is an engineering challenge all by itself. They have to fly everyone in and out of the site on small planes and bring in all their food and supplies on giant road trains. Safety is another major part of the engineering plan, especially when dealing with radioactive material. The ore contains thorium and uranium, which means the waste left over after processing is a bit dangerous. To keep it safe, the engineers are building massive ponds called residue storage facilities. These ponds have very thick plastic liners and layers of clay to make sure no chemicals or radioactive materials can leak into the ground or the water. They also use special monitors to check the air for a gas called radon, which can be released when you dig up uranium. Every worker wears a small badge that measures how much radiation they are exposed to every day to make sure they stay healthy. The engineers have calculated that a worker will get about 2.1 millisieverts of radiation a year, which is well within the safe limits for people working in mines. So, with all this incredible technology and planning, what could possibly go wrong? The project is facing some big questions about the environment and the cost. Some people in the local community and environmental groups are worried that the mine will use too much water from the underground basins, which could hurt the local plants and animals. There is also the huge cost of $2.6 billion to build everything. While the Australian government is providing $840 million in loans, and the National Reconstruction Fund is putting in $200 million, the company still needs to find more investors to pay for the rest. Some critics point out that the project has been in development for over 20 years and still has not finished building the main plant. But with car companies like Hyundai, Kia, and Siemens Gamesa signing big contracts to buy the rare earths, the pressure to finish is higher than ever. Construction is expected to ramp up by the start of 2026, and if everything works, this one mine will provide about 4% of the world's rare earth magnets by 2032. It is amazing to think that the future of our electric cars might depend on a vibrating filter and a giant hole in the Australian desert. Do you think building a mine like this is the right move for the environment, or are the risks too high? Let us know what you think in the comments below and turn on your notifications so you never miss a video. If you want to see more deep dives into the engineering that powers our world, make sure to hit the like button and subscribe to our channel. Thanks for watching and see you in the next one.